What are you? Right now, as you read these words, you're actually performing an act of incredible complexity. Information flows from this screen through your eyes and into the intricate network of your brain. Your mind processes the shapes of these letters, converts them into sounds, and assembles them into concepts. This is intelligence. It is computation. A powerful enough computer, a sophisticated artificial intelligence, could perform this very same task. It could read, analyze, and even summarize this text with breathtaking speed and accuracy. But would it anything while doing so? Would there be an inner, private experience of understanding? This is the chasm that separates mere information processing from the subjective reality of consciousness, the internal movie that you are living right now. For decades, the prevailing assumption has been that consciousness is an emergent property of complex computation. The idea is that if you build a system with enough interconnected nodes and processing power, consciousness will simply switch on like a light bulb finally receiving enough current. In this view, the brain is a biological computer, a wetware machine running a sophisticated program. Your thoughts, your emotions, your sense of self, all are believed to be the output of this program. The material it runs on, whether silicon chips or carbon-based neurons, is considered irrelevant. It is the pattern, the algorithm, the software that matters. But a profound and challenging idea from one of the world's most brilliant minds suggests this view might be fundamentally incomplete. This alternative proposes that consciousness is not just about the complexity of the connections, but about the very fabric of reality in which those connections exist. It argues that a crucial piece of the puzzle lies not in computer science, but in fundamental physics, specifically in gravity. This isn't the familiar gravity that pins us to the Earth, but a subtle quantum-level effect that might govern the collapse of possibilities into a single, definite reality. The theory suggests that consciousness is tied to a physical process that today's computers cannot, and perhaps never can, simulate. It hints that the feeling of awareness is a feature of the universe itself, harnessed by the delicate, specific architecture within our neurons. This idea places a ghost back into the machine, but it's not a supernatural one. It is a ghost woven from the laws of physics, from the strange and counterintuitive rules of the quantum world. This perspective shifts the entire debate. It asks us to consider that the hardware isn't interchangeable after all. It suggests that the unique biological material of the brain is not just a convenient platform for computation, but is instead a finely tuned instrument designed to interact with the universe in a way that silicon chips cannot. The question then becomes monumental. Is your mind a product of pure code, or is it a conduit for a deeper gravitational reality? The answer could redefine not only ourselves, but the future of intelligence itself. To draw a clear line in this debate, we must first agree on our terms. When we talk about consciousness, we're not merely talking about intelligence or behavior. A self-driving car is intelligent. It perceives its environment, makes decisions, and acts upon them. Yet, we have no reason to believe it has an inner life. It doesn't the sunlight on its sensors or the rumble of the road through its tires. This internal, subjective experience, the redness of red, the sweetness of a strawberry, the sting of a memory, is what philosophers call qualia. It is the essence of what we are trying to explain. It's the difference between a machine that can write a perfect sonnet about love and a human who has actually felt it. The dominant scientific theories of consciousness, such as the global neuronal workspace, or GNW theory, focus on the computational architecture of the brain. GNW proposes that you become conscious of a piece of information when it is broadcast across a widespread network of neurons, making it available for various cognitive processes like memory, planning, and language. In this model, consciousness is a functional property of information access. If information is globally available, it is conscious. If it is confined to a local processing module, it remains unconscious. This is a powerful and elegant framework that aligns beautifully with our understanding of the brain as an information processing system. It suggests consciousness is a clever trick of data management. Another leading computational model, integrated information theory, or IIT, takes a slightly different but related approach. IIT posits that consciousness corresponds to a system's capacity to integrate information. It attempts to quantify this with a mathematical value called phi. A system with high phi, like the human brain, has a structure where the whole is vastly more than the sum of its parts. Its components are richly interconnected and interdependent. A system with low phi, like a digital camera's sensor array, has components that act largely independently. For IIT, consciousness integrated information. The higher the integration, the more conscious the system. Both GNW and IIT are hardware agnostic. They care about the pattern of connections, not the stuff being connected. These theories are compelling because they're testable and provide a clear path forward for building artificial intelligence. They imply that if we can replicate the brain's functional architecture, its global workspace, or its integrated information structure, in a silicon-based machine, we will have created genuine consciousness. The machine would not just be an inner life, it would actually have one. This is the orthodox view, the bedrock upon which most of modern neuroscience and AI research is built. It's a clean, elegant, and purely computational story. But what if a fundamental force of nature, one we've overlooked in this domain, refuses to be ignored? What if the stuff matters more than we ever imagined? The radical alternative, championed most famously by the mathematical physicist Sir Roger Penrose, argues that the computational story is missing the most important chapter. Penrose contends that human understanding, particularly our ability to grasp mathematical truths, possesses a quality that cannot be captured by any algorithm. He argues that consciousness must involve a non-computable process, something that lies outside the realm of classical and digital machines. This is not a philosophical preference, but a conclusion he draws from the deep logic of mathematics and computation, particularly Gödel's incompleteness theorems. If consciousness is indeed non-computable, then it cannot emerge from a brain that is merely a complex computer. It must be tapping into something else. This something else Penrose proposes is the physics of reality at its most fundamental level. Specifically, he points to the unresolved mystery of quantum mechanics, the measurement problem. In the quantum world, particles can exist in multiple states at once. A superposition. This blurry state of potential persists until a measurement is made, at which point the system collapses into one single definite reality. Mainstream interpretations have struggled to explain what constitutes a measurement. Penrose suggests that it is not an external observer, but gravity itself that resolves this ambiguity. He posits that every superposition has a tiny amount of mass energy associated with it, creating a minuscule warp in spacetime. When this warp reaches a certain threshold, it becomes unstable and collapses on its own. This process, called objective reduction, or OR, is a proposed physical law, not just an interpretation. It suggests that reality is constantly choosing its state based on a gravitational trigger. The theory, developed with anesthesiologist Stuart Hameroff, is called orchestrated objective reduction, or Orch-OR. It hypothesizes that this gravity-induced collapse is not random noise but is orchestrated within the brain, specifically inside tiny protein structures within our neurons called microtubules. These microtubules, the theory claims, can sustain quantum superpositions long enough for them to reach the gravitational collapse threshold. Each moment of orchestrated collapse, according to Orch-OR, corresponds to a moment of conscious experience. Here, then, is the line in the sand. On one side, we have the computational theories, GNW and IIT, which state that consciousness is a pattern of information flow, independent of the physical substrate. On the other side, we have Orch-OR, which claims consciousness is a specific, non-computable physical process intimately linked to quantum gravity, occurring within a unique biological structure. This is not just a philosophical disagreement. It is a clash of two fundamentally different views of the universe and our place within it. For the first time, this clash presents us with a possibility that was once unthinkable, a clean, falsifiable experiment. A test that could distinguish gravity from code and finally begin to answer the most profound question we can ask. Before we venture into the exotic world of quantum gravity, we must first understand the reigning paradigm, the powerful and elegant idea that consciousness is, at its core, a product of computation. This viewpoint begins with a simple, yet profound observation. The brain is an information processing machine. It takes in sensory data, recognizes patterns, accesses memories, and generates outputs in the form of thoughts, emotions, and behaviors. In this framework, the mind is what the brain, the intricate dance of 86 billion neurons firing in complex sequences, is seen as a form of biological computation, different in its wet substrate, but not fundamentally different in its logical principles from the silicon chips inside your smartphone or a data center's vast server racks. This computational view is deeply rooted in the scientific materialism that has successfully explained so much of our world. It treats the brain as a physical system governed by the known laws of chemistry and electricity. There's no need for mysterious, non-physical forces or souls to explain the mind. Instead, consciousness is considered an emergent property. Much like the intricate patterns of a flock of birds emerge from the simple rules followed by each individual bird. No single neuron is conscious, just as no single bird understands the concept of a murmuration. But when you put enough of them together, connected in just the right way, a new, higher-level phenomenon, conscious awareness, is believed to simply switch on. The core appeal of this perspective is its straightforward, mechanistic nature. It suggests that if we can fully map the brain's connectomy, the complete wiring diagram of all its neural connections, and understand the rules of its signal processing, we can replicate it. Consciousness, in this model, is substrate independent. It doesn't matter if the logic gates are made of proteins and lipids or silicon and copper. As long as the computational architecture is the same, the resulting experience should be the same. This is the foundational belief that drives much of modern artificial intelligence research, that building a truly conscious machine is not a question of, but of our processing power and architectural understanding becomes sufficiently advanced. Therefore, the central task for a computational theory of consciousness is to identify which specific type of computation or information architecture gives rise to subjective experience. What is the special algorithm that our brain is running? The search for this consciousness code has led to several sophisticated and compelling theories. They don't seek new laws of physics. Instead, they look closely at the brain's known structure and function, attempting to pinpoint the precise data handling trick that separates the lights-on awareness of a waking mind from the dark, silent processing of a computer running its background tasks. These theories provide the essential baseline against which any alternative like Penrose's gravity-based model must compete. One of the most prominent computational theories is the Global Neuronal Workspace, or GNW. So imagine your brain as a massive organization full of specialized departments. There's a visual department, an auditory department, a memory archive, a language center, and, a planning committee. Most of the time, these departments work locally, processing their own data without bothering the rest of the organization. This is what we call unconscious processing. For example, you can walk down the street while your motor cortex handles the complex mechanics of balance and gait, all without your conscious involvement. But what happens when something truly important occurs, like a car horn blaring or someone calling your name? That specific piece of information needs to be shared with everyone. GNW proposes that consciousness is what happens when information goes viral within the brain. A piece of sensory data, or maybe an internal thought, gains access to a central broadcasting system, a global workspace, composed of a network of long-range neurons, primarily in the prefrontal and parietal cortices. Once information enters this workspace, it is broadcast widely across the entire brain, becoming available to all the specialized departments. Your language center can now report on it. I hear a horn. Your memory department can search for context. That sounds close. And your planning committee can generate a response. I should jump back onto the sidewalk. According to GNW, this state of global information availability consciousness. This model makes clear, testable predictions. Neuroscientists can look for signatures of this global ignition. When a person becomes aware of a visual stimulus they were previously ignoring, we should see a sudden coordinated burst of activity across this widespread brain network. And that is precisely what brain imaging techniques like EEG and fMRI have shown. Unconscious stimuli trigger localized activity, but the moment of conscious recognition is accompanied by a late, large-scale brain signal. The theory provides a functional, concrete mechanism for what it means to be aware of something. It means that information has won a competition for access to the global stage of the mind. Crucially, GNW is entirely about architecture and information flow. It makes no special claims about the underlying physics. Any system, biological or artificial, that implements this architecture of specialized processors linked by a global broadcasting hub should, in principle, become conscious. If we were to build a robot with a similar cognitive architecture, it would report on its inner states, not because it was programmed to mimic a human, but because its internal information was being handled in the same globally accessible way. In the GNW view, the ghost in the machine is not a ghost at all, it's simply the executive summary delivered to the entire company at once. A second highly influential computational theory approaches the problem from a different, more philosophical angle. This is integrated information theory, or IIT. Instead of asking what consciousness, IIT starts by asking what consciousness. It identifies the essential properties of our own subjective experience. Every moment of consciousness is rich with detail. And yet it is experienced as a seamless, unified whole. You don't experience the color red separately from the shape of a ball. You experience a unified red ball. IIT proposes that any physical system that possesses these twin properties of information and integration must, by definition, be conscious. To formalize this, IIT introduces a mathematical measure called phi, or F. Phi quantifies the degree to which a system as a whole is more than the sum of its parts. A system with high phi is one where its components are so densely and cleverly interconnected that you cannot understand the state of the system by looking at its parts in isolation. The brain, with its massive interconnectivity, is a prime candidate for a high phi system. In contrast, a system like a digital camera sensor has millions of pixels, but each one is largely independent. Its phi value would be very low. For IIT, consciousness is not an all-or-nothing affair. It's a gradient. The higher a system's phi, the more conscious it is. This provides a powerful, if abstract, framework. It suggests we could, in theory, build a consciousness meter that could measure the phi of any system, a human brain, a cat's brain, a smartphone, or even the internet, and assign it a value corresponding to its level of experience. Like GNW, IIT is fundamentally substrate independent. It doesn't care about quantum mechanics or special biological properties. It cares only about the causal structure of the system, the fabric of cause and effect woven by its interconnected components. If a silicon-based AI could be built with a sufficiently high phi value, IIT would state that it is undeniably conscious, possessing its own genuine inner experience. The implications are staggering. IIT suggests that consciousness might be a far more widespread property of the universe than we typically assume. Any system with the right kind of integrated information structure would have some degree of experience, however minimal. This theory grounds consciousness in the mathematics of cause and effect structures, turning it from an elusive philosophical mystery into a quantifiable physical property. It defines the problem with beautiful precision. Offering a clear computational target to build a conscious machine, we must build a machine with a high value of phi. The challenge is purely one of engineering the right information architecture. Both the global neuronal workspace and integrated information theory are masterpieces of scientific reasoning, providing compelling, testable frameworks for understanding the mind. They represent the intellectual summit of the computationalist viewpoint. Yet, for all their differences in approach, one focusing on function, the other on structure, they are built upon a shared foundational assumption. This assumption is that the classical laws of physics are sufficient. They model neurons as nodes in a network that are either on or off, firing or not firing, and communicating via signals that follow predictable, deterministic paths. In this world, there is no room for fundamental randomness or quantum ambiguity. This assumption is perfectly reasonable. At the scale of a single neuron, classical physics and chemistry appear to describe its behavior with incredible accuracy. The flow of ions across a membrane, the release of neurotransmitters, the propagation of an electrical signal down an axon. All of these processes seem to be well understood, computable phenomena. The standard view is that any quantum effects that occur at the subatomic level are quickly washed out by the noisy, warm, and wet environment of the brain, a process known as decoherence. They are irrelevant statistical noise, not a meaningful part of the signal. The brain's computation, therefore, can be effectively modeled as a classical system. This is the bedrock on which the entire edifice of computational neuroscience and artificial intelligence is built. It is the belief that if you had a supercomputer powerful enough to simulate every single atom in a brain according to the known laws of classical physics and chemistry, you would inevitably simulate the emergence of a conscious mind. The simulation would not just claim to be conscious, it would conscious, because it would be perfectly replicating the information processing pattern that gives rise to experience. The hardware, whether wetware or software, is merely the platform for the all-important pattern. But it is precisely this unspoken assumption that Sir Roger Penrose challenges. He argues that by dismissing the quantum world as irrelevant noise, we may be throwing out the most critical piece of the puzzle. What if the brain is not a classical computer at all? What if it is instead a quantum computer, harnessing the strange logic of superposition and collapse to achieve something that no classical machine ever could? This question marks the dramatic departure from the mainstream. It suggests that to understand the mind, we must look beyond the elegant logic of information and face the deep, unresolved mysteries at the very foundation of physics itself. The journey into the quantum mind begins not in a biology lab, but in the abstract realm of pure mathematics. It starts with Sir Roger Penrose, a figure whose work on black holes and the structure of space-time earned him a Nobel Prize. Penrose's skepticism about the computational theory of mind stems from a deep conviction that human understanding operates in a way that transcends formal algorithms. He points to Gödel's incompleteness theorems, which prove that in any sufficiently complex mathematical system, there will always be true statements that cannot be proven within that system's own rules. Yet, human mathematicians can often perceive the truth of these unprovable statements through a flash of insight or understanding. This, for Penrose, is a critical clue. He argues that this ability to see mathematical truth beyond the confines of a formal system suggests that the human mind is not itself a formal system. If the brain were just a computer running an algorithm, it would be bound by the same Gödelian limits as any other machine. It would have its own set of unprovable truths that it could never access. But our capacity for genuine, flexible understanding points to something more. Penrose concludes that whatever consciousness is, it must be non-computable. It must harness some physical process that cannot be simulated by a standard digital computer, no matter how powerful. This is a bold and profound claim, as it seeks to place the mind outside the entire framework of modern computation. This objection fundamentally reframes the problem. Instead of asking what kind of computation creates consciousness, Penrose asks what physical process in the universe is non-computable, and could the brain be using it? The answer, he believes, lies in the most mysterious and poorly understood corner of physics, the intersection of quantum mechanics and gravity. He proposes that the very act of consciousness is tied to the process by which the fuzzy, probabilistic world of quantum possibilities collapses into the single, concrete reality we experience. This isn't just a philosophical preference. It's a search for a physical mechanism that could explain the unique, non-algorithmic nature of human thought. This line of reasoning places Penrose at odds with the vast majority of neuroscientists and AI researchers. It suggests that the quest to build a conscious machine by simply writing more complex software is doomed to fail. If he is right, no algorithm, no matter how sophisticated, can ever achieve genuine understanding because it is playing a different game entirely. The brain isn't just processing information, it is tapping into the fundamental process of physical reality's creation. The search for consciousness, then, must leave the world of pure information and venture into the strange physical machinery operating at the quantum scale within our own neurons. The brain is to harness a non-computable quantum process. It needs a place for that process to occur. The conventional view of neurons, as simple on or off switches firing in a noisy, classical environment, just won't do. Quantum states are notoriously fragile. The slightest thermal vibration or interaction with the environment can destroy them in a process called decoherence. The warm, wet, and chaotic interior of a living cell seems like the last place one would expect to find delicate quantum effects at work. This is the warm, wet brain objection, and it is the single greatest challenge for any theory of quantum consciousness. A suitable location must be found that is somehow shielded from this environmental noise. This is where Stuart Hameroff, an anesthesiologist and consciousness researcher, enters the story. He proposed that the perfect candidates for hosting these quantum computations are the microtubules. These are tiny, cylindrical protein polymers that form the cytoskeleton or structural scaffolding of every cell, including neurons. For a long time, they were thought to be simple structural supports, like the girders in a building. But Hameroff argues they are far more sophisticated. He suggests they are information processing devices in their own right, acting as the nervous system within the neuron. Their hollow, crystalline structure and the materials they are made of, he claims, could create an environment isolated enough to protect quantum states from the chaos of the cell. Microtubules are built from small, peanut-shaped proteins called tubulin. Each tubulin protein can switch between at least two different shapes, driven by the location of tiny quantum particles within it, known as electrons. According to the theory developed by Penrose and Hameroff, orchestrated objective reduction, or Orch-OR, these tubulin proteins can enter a quantum superposition, existing in both shapes at once. Furthermore, they propose that these individual superpositions can link up, becoming quantumly entangled with their neighbors along the microtubule. This would create a large coherent quantum state, a form of quantum computation, unfolding within the very skeleton of the neuron, shielded from the noisy cellular environment. This is a radical reimagining of cellular biology. It elevates the microtubule from a passive structural element to the active computational core of the neuron. Instead of the neuron being a simple switch, it becomes a quantum computer, running complex calculations inside its own internal framework. Each neuron, in this view, is vastly more powerful than a simple bit in a digital computer. The brain is not just a network of 86 billion switches, but a network of 86 billion quantum processors, each containing countless quantum bits. This provides the necessary biological hardware for Penrose's non-computable process, setting the stage for the most crucial element of the theory, the role of gravity. Having proposed a location for quantum computation, the microtubules, Orch-OR needed a mechanism to connect this computation to conscious experience. This is where Penrose's core idea about quantum gravity comes into play. In standard quantum mechanics, the collapse of a superposition into a definite state is a major puzzle. It seems to happen whenever a quantum system is measured or observed, but what constitutes a measurement is not clearly defined. Penrose offers a radical solution. A measurement is not needed. Instead, gravity itself resolves the ambiguity. This proposed mechanism is called objective reduction, or OR, because it is an objective, observer-independent process. The theory links quantum mechanics to Einstein's general relativity. According to Einstein, mass and energy curve the fabric of space-time. This curvature is what we feel as gravity. Penrose argues that when a particle is in a superposition of being in two places at once, it creates two slightly different curvatures in space-time. For a brief moment, space-time itself is in a superposition, a tiny blister of ambiguity. He posits that the universe does not tolerate this state of affairs for long. This separation of space-time from itself creates a gravitational self-energy, a kind of instability. When this energy reaches a critical threshold, the system becomes unstable and spontaneously collapses into one single definite state with no measurement required. This leads to a beautiful and simple equation. Tau equals hbar divided by Eg. Here, tau is the time it takes for the superposition to collapse on its own. H-bar is the reduced Planck constant, a fundamental number in quantum mechanics, and Eg is the gravitational self-energy of the superposition, a measure of how much the two separated versions of the mass particle are pulling space-time apart. The equation shows that the lifetime of a superposition is inversely proportional to its gravitational energy. A larger, more spread-out superposition with a higher Eg will collapse faster. A smaller, more compact one will last longer. This provides a physical, non-random clock for the universe's state selection process. This is the heart of the physical claim. It proposes a new law of nature that bridges the gap between the quantum world and the world of gravity. It asserts that there is a specific calculable timescale for the collapse of any given superposition determined by its mass distribution. This isn't just a philosophical interpretation, it's a concrete physical hypothesis. If true, it means that gravity, the force that shapes galaxies and orbits, also plays a fundamental role in shaping reality at the smallest scales. And according to Orch-OR, it is this very process, happening over and over inside our brains, that creates the flow of our conscious thoughts. So, the final step here is to connect the physics of objective reduction to the biology of microtubules. The Orch-OR theory proposes that quantum superpositions of tubulin proteins within microtubules are the source of the gravitational self-energy, which is called E-G. As more and more tubulins join this coherent quantum state, the total mass involved in the superposition grows, and the Eg value increases. According to the equation tau equals h-bar divided by Eg, this means the collapse time, tau, actually gets shorter. The theory suggests this process continues until tau reaches a timescale that's relevant to neural processes, like, for example, around 25 milliseconds, which matches up with those 40 Hz gamma band brainwaves that are often linked to conscious perception. When the collapse threshold is reached, the quantum state inside the microtubules undergoes objective reduction. It snaps from a state of multiple possibilities into a single, definite classical state. And according to the theory, this physical event, this moment of gravity-induced collapse, is a moment of conscious experience. It's like a discrete frame in the movie of your consciousness. The continuous flow of our awareness is proposed to be a sequence of these individual, objective collapse events, kind of like the frames of a film reel. Now, the orchestrated part of the name refers to the idea that this process isn't just random. It's guided, or orchestrated, by the computations happening within the microtubules, which select specific outcomes that end up influencing neuronal firing. This model, honestly, provides a narrative for how consciousness happens. It starts with sensory input or internal processing triggering quantum superpositions in microtubule tubulins. These superpositions evolve and compute, linking up and growing until they reach the Penrose OR threshold. At that point, gravity intervenes, collapses the state, and a moment of conscious awareness occurs. This collapse then influences the classical behavior of the neuron, causing it to fire or not, and that in turn affects the rest of the brain's network. So, consciousness, in this view, is not just an emergent property of complex classical computation, but an intrinsic feature of the universe, a sequence of discrete physical events tied to quantum gravity, harnessed and orchestrated by our neural architecture. It's a breathtakingly ambitious synthesis of neuroscience, quantum physics, and cosmology. It paints a picture of the mind as a finely tuned instrument, playing a cosmic symphony where the notes are moments of reality itself being chosen. It suggests that each conscious moment is a selection from a platter of quantum possibilities. A selection governed not by random chance, but by a deep connection between the matter in our heads and the geometry of space-time. This is no longer just a theory of the brain. It's a theory of reality, with the conscious mind playing a central active role. The most profound implication of the Orch-OR theory is that consciousness, if it really does arise from this process, is fundamentally non-computable. The reason for this lies in the nature of objective reduction itself. The outcome of the collapse is not determined by an algorithm. While the evolution of the quantum state before the collapse is, sure, computable via the Schrödinger equation, the collapse itself, according to Penrose, contains a non-algorithmic element. He speculates that this might involve influences from the very structure of space-time geometry, a level of physics that's just not representable by any Turing machine. In this view, the universe isn't just carrying out a massive computation, it's doing something more, something that involves a form of understanding that's embedded in its physical laws. This non-computability, Penrose believes, is what accounts for the special quality of human insight, creativity, and mathematical intuition. A digital computer, no matter how powerful, operates by executing a predefined set of rules, an algorithm. It simply can't step outside those rules. If Orch-OR is correct, then the brain is not bound by such rules. Each moment of gravity-induced collapse taps into this non-computable physics, allowing for genuine flashes of insight that aren't just the logical output of a previous state. This would mean that human consciousness possesses a quality that artificial intelligence, as we currently conceive it, could never replicate. We could build machines that are incredibly intelligent, but we could never program them to be truly conscious. This creates a stark, dramatic dividing line between humans and machines. In the computationalist view, like GNW and IIT, consciousness is a difference of degree. A sufficiently complex machine could cross the threshold, but in the Penrose-Hameroff view, it's a difference in kind. Consciousness depends on a specific physical process tied to quantum gravity, a process that is likely impossible to simulate. This would elevate biological life, or at least life with microtubule-like structures, to a special place in the cosmos. It would mean that the stuff we're made of is not just incidental, but actually essential to the nature of our minds. Our carbon-based biology would be a requirement, not just a historical accident. So the debate really boils down to a fundamental question about the nature of reality. Is the universe a giant computer and the brain just a smaller one running a special program we call consciousness? Or is the universe something more? A place where the laws of physics include a non-computable element of spontaneous state selection, a process that the brain has uniquely evolved to harness? For decades, this has been a fascinating but largely philosophical debate. For decades, the chasm between computational and quantum theories of consciousness seemed totally unbridgeable, a domain of pure philosophical debate. Proponents of models like GNW and IIT argued that consciousness is all about the pattern of information, while Orch-OR proponents claimed it was about a physical process tied to gravity. But without a way to actually test these competing claims, the conversation stayed kind of stuck. I mean, how could you possibly design an experiment to distinguish between a complex algorithm and a gravity-induced quantum collapse happening deep inside a neuron? The beauty of the Orch-OR theory, though, is that its radical nature contains the seeds of its own potential falsification. It makes a very specific, very physical, and therefore very testable prediction. The key lies in the central equation of objective reduction tau equals hbar divided by Eg. This equation says that the time it takes for a conscious moment to occur, tau is directly dependent on the gravitational self-energy, Eg, of the superposition. This energy, in turn, depends on the amount of mass involved and how far it's separated from itself in the superposition. So, this gives us a crucial variable that, in principle, we can manipulate mass. If we could find a way to subtly change the mass of the components involved in the supposed quantum state without changing anything else about the system's chemistry or computational structure, we could see if it affects the timing of conscious processes. And this is the experimental showdown we've all been waiting for. This leads to the design of what we can call the mass invariance test. The logic here is beautifully simple. First, you identify a neural correlate of consciousness, a measurable brain activity that's tightly linked to conscious experience. A prime candidate is the 40 Hz gamma band brainwave, which Orch-OR specifically associates with the frequency of its collapse events. A 25 millisecond collapse time corresponds to a 40 Hz frequency. Then, you run the experiment under two conditions. In the control condition, the brain operates normally. In the test condition, you increase the mass of the specific molecules that Orch-OR claims are creating the superposition, namely the tubulins within the microtubules. The crucial constraint is that this mass change must be the only significant change. The chemistry, the electrical properties, and the overall structure of the neurons have to remain identical. If consciousness is purely computational, as GNW and IIT suggest, then this subtle change in nuclear mass should have no effect. The brain's algorithm doesn't care about the weight of the atoms carrying the bits, only about the logic of their interactions. But if Orch-OR is correct and consciousness is tied to gravitational collapse, then increasing the mass should increase the gravitational self-energy, Eg, which in turn should shorten the collapse time, tau, leading to a measurable change in the frequency of conscious moments. So how can we possibly increase the mass of tubulin proteins inside a living neuron without altering their chemical function? The answer lies in a clever biological trick using isotopes. Isotopes are versions of an element that have the same number of protons but a different number of neutrons. This means they have a different atomic mass but nearly identical chemical properties. For example, the most common form of carbon is carbon-12 with 6 protons and 6 neutrons. But there is also a stable, heavier isotope, carbon-13, which has an extra neutron. A molecule built with carbon-13 will be slightly heavier than its normal counterpart, but it will form the same chemical bonds and participate in the same biochemical reactions. The experimental strategy, then, is to enrich the building blocks of tubulin proteins with heavier isotopes. We could raise organisms or prepare brain slices in an environment where the essential amino acids used to build proteins are synthesized with carbon-13 or nitrogen-15 instead of their lighter, more common isotopes. This process, known as isotopic labeling, would result in microtubules that are physically heavier but chemically and structurally unchanged. This is, honestly, the perfect tool for our mass invariance test. It allows us to tweak the very parameter, mass, that Penrose's theory depends on, while leaving the computational architecture of the neuron, which the other theories depend on, almost completely untouched. Of course, we must be incredibly careful. The experiment needs to be designed to isolate the effect of mass alone. It wouldn't be enough to simply make the entire brain heavier, as this could have all sorts of secondary metabolic effects. The Orch-OR theory is specific. It's the mass of the part that is moving in the superposition that matters. The theory posits that certain parts of the tubulin protein shift by a tiny distance. The ideal experiment would therefore only enrich those specific mobile regions of the protein with heavier isotopes, leaving the stationary parts with their normal isotopic composition. This is a formidable biochemical challenge, but it represents the cleanest possible version of the test. With this setup, we have two brains, or two brain slices, ready for comparison. One is the control, built from standard light isotopes. The other is the test subject, with its microtubules weighed down by heavy isotopes in key locations. Both are functionally and chemically identical. Both are presented with the same stimuli designed to elicit a conscious response. We then hook them up to an electroencephalogram or a more direct neural probe and measure the resulting brain activity. The stage is set for a direct confrontation between the two rival paradigms of consciousness. The data from our instruments will now serve as the judge. Let's walk through the prediction made by the Orch-OR theory. It is direct, quantitative, and unambiguous. In the control brain, with its normal mass microtubules, the quantum superpositions of tubulin proteins will evolve, accumulating gravitational self-energy, e.g., until they reach the collapse threshold at time tau. The theory posits this tau is about 25 milliseconds, giving rise to the familiar 40 Hz gamma rhythm associated with consciousness. This is our baseline. Now, we turn to the brain with the isotopically enriched microtubules. These tubulins are heavier. When they enter superposition, the amount of mass being separated from itself is greater than in the control case. This increased mass directly leads to a larger gravitational self-energy, ERG. According to the Penrose equation, tau equals hbar divided by EEG. Since EEG is now larger, the collapse time tau must become shorter. A shorter collapse time means that the moments of conscious experience are occurring more frequently. If the baseline frequency was 40 Hz, one collapse every 25 milliseconds, a shorter tau, say 24 milliseconds, would correspond to a new, higher frequency of about 41.7 Hz. The prediction of Orch-OR is therefore crystal clear. The subject with the heavier microtubules should exhibit a small but measurable increase in the frequency of their gamma band brainwaves during conscious processing. The magnitude of this frequency shift can even be estimated. It depends on several factors, including what fraction of the tubulin protein's mass is in superposition and how much heavier the isotopes make it. Using reasonable estimates from the model, the predicted frequency shift might be on the order of 1 to 3%. While small, this is well within the detection capabilities of modern neurophysiological recording equipment, provided the experiment is conducted with sufficient precision and statistical power. The theory doesn't just predict a generic change, it predicts a specific direction, an increase in frequency, and a plausible magnitude. This is the hallmark of a strong, falsifiable scientific hypothesis. This result, if observed, would be a seismic event in science. It would provide the first ever experimental evidence that a quantum gravitational process is happening within the brain and is directly linked to the timing of conscious experience. It would be a stunning vindication for the Penrose-Hameroff model and would shatter the purely computational paradigm. It would mean that consciousness is not an algorithm running on arbitrary hardware, but a fundamental physical process that intimately depends on the mass of the particles in our neurons. The ghost in the machine would have been found, and its shadow would have a measurable weight. Now, let's consider the alternative outcome. What do the prevailing computational theories, GNW and IIT, predict for the mass invariance test? Their prediction is just as clear and, in its own way, just as powerful. Nothing should happen. From the perspective of a computational theory, the mass of the atoms is simply an implementation detail, like the brand of silicon used to fabricate a microchip. As long as the logic gates function correctly, the underlying hardware's weight is irrelevant. The brain's algorithm, whether it's a global broadcast or a measure of integrated information, is defined by the pattern of connections and the flow of signals, not by the nuclear mass of the carbon atoms in its proteins. In the GNW model, consciousness occurs when information is broadcast across a specific neural network. The speed and success of this broadcast depend on factors like synaptic strength, neural firing rates, and the overall connectivity of the workspace, not the mass of the microtubules inside the neurons. Changing the isotopic composition of tubulin should not affect any of these parameters. The neurons will still fire, the signals will still propagate, and the information will still be broadcast. Therefore, GNW predicts that the gamma band frequency and any other neural correlate of consciousness should remain completely unchanged between the control and the isotope-heavy subject. The result should be mass invariant. Similarly, for integrated information theory, consciousness corresponds to the value of phi, a measure of a system's causal irreducibility. This value is determined by the system's architecture, the intricate web of cause and effect among its components. While a massive change in mass could theoretically alter signal propagation times, the subtle shift from isotopic labeling is designed to be negligible in this regard. The causal structure of the neural network remains identical. The same neurons are connected to the same partners with the same strengths. Therefore, the integrated information, phi, should not change. IIT, like GNW, predicts a null result. The experiment should show no difference in the neural signatures of consciousness. This null result would be just as profound as a positive one. If a carefully conducted experiment with sufficient power to detect a small effect shows no frequency shift, it would be a major blow to the Orch-OR hypothesis. It would strongly support the computationalist viewpoint, suggesting that we are on the right track when we model the brain as a complex biological computer. The burden of proof would fall squarely back on those who claim that new physics is required to explain the mind. The mass invariance test thus creates a perfect fork in the road. One path leads to a revolution in physics and neuroscience, the other reinforces the foundations of modern AI and cognitive science. Before we rush to the lab to run our mass invariance test, we really have to confront the towering objection that has faced the Orch-OR theory since its inception. This is the decoherence argument, often summed up with the evocative phrase, "The brain is just too warm, wet, and noisy to support the delicate quantum phenomena that Orch-OR requires." Quantum states, like the superpositions proposed to exist in microtubules, are, well, notoriously fragile. A single stray photon, a thermal vibration, or even a collision with a water molecule can be enough to destroy the quantum coherence, collapsing the superposition into a classical state prematurely and randomly. This process, known as environmental decoherence, is honestly the bane of quantum computing. Critics, most notably the physicist Max Tegmark, have performed calculations suggesting that the decoherence timescale inside a neuron would be astonishingly fast, on the order of femtoseconds or even faster. That's millions of times shorter than the 25 millisecond timescale Orch-OR requires for its gravity-induced collapse to correspond with 40 Hz gamma waves. If these calculations are correct, any quantum superposition in a tubulin protein would be destroyed by the chaotic thermal environment of the cell almost instantly. It would be like trying to hear a whisper in the middle of a rock concert. The quantum signal would just be drowned out by classical noise long before it could ever grow large enough to be orchestrated or reach the Penrose gravitational threshold. This argument strikes right at the very heart of the theory's biological plausibility. It suggests that even if Penrose's physics of objective reduction is correct, the brain is simply the wrong kind of environment to make use of it. Proponents of the standard computational models argue that this is precisely why they are more credible. They rely only on robust, classical, electrochemical processes that are known to operate effectively in the brain's messy environment. They don't need to invoke exotic, fragile quantum states that seem to violate our understanding of thermodynamics and cellular biology. For these critics, the decoherence problem is not just a minor hurdle for Orch-OR, it is honestly a fatal flaw. Therefore, any defense of the quantum mind has to provide a compelling answer to this challenge. It's not enough to have a beautiful theory about gravity and consciousness. You also have to explain how the biological hardware could possibly protect its quantum operations from the relentless onslaught of decoherence. The theory needs a shield. It must propose a plausible biological mechanism by which microtubules can isolate their quantum computations from the warm, wet chaos surrounding them, preserving their coherence for timescales that are orders of magnitude longer than physicists would normally expect. The entire viability of the Orch-OR model really hinges on this crucial biological detail. The proponents of Orch-OR have not ignored the decoherence challenge. Stuart Hameroff and his collaborators have actually put forward several counter-arguments and proposed mechanisms that could, at least in theory, fend off the thermal noise of the cell. Their primary defense centers on the specific structure and environment of the microtubule itself. They argue that the initial damning calculations made by critics like Tegmark were based on oversimplified models that just didn't capture the true biological complexity of the system. The microtubule, they contend, isn't just a passive structure floating in the cellular soup. It's a highly organized and potentially shielded environment, uniquely suited for protecting quantum states. One key proposal is that the tubulin proteins within the microtubule lattice do not act independently, but in a collective, synchronized manner. The superpositions might be distributed across many tubulins in a way that makes them more robust to local disturbances, a concept known as collective excitation. Furthermore, they suggest that the interior of the microtubule cylinder might be filled with a special, ordered form of water. This ordered water, they claim, could act as an insulating sheath, creating an electrically isolated channel down the core of the microtubule, shielding the quantum states within the tubulin proteins from the noisy electrical fluctuations in the surrounding cytoplasm. Another part of the shielding hypothesis involves the very speed of the proposed quantum computations. Hameroff suggests that the processing within the tubulins could occur at extremely high frequencies in the gigahertz to terahertz range. This would mean that many computational steps could take place before decoherence has a chance to set in. The idea is that the quantum state is processed and built up so rapidly that it basically outruns the environmental noise. They also point to the discovery of quantum effects in other warm, wet biological systems, such as photosynthesis, where quantum coherence plays a demonstrable role in energy transfer, proving that nature has found ways to protect quantum processes from decoherence. These counter-arguments transform the debate from a simple yes or no into a far more nuanced discussion about the precise biophysics of the microtubule. Are microtubules truly capable of this level of shielding? Is water inside them ordered in a special way? Can tubulins act in a coherent, collective manner? These are now open, empirical questions that can be investigated through advanced microscopy and biophysical experiments. While the shielding hypothesis remains controversial and is, honestly, far from proven, it provides a plausible, if speculative, path forward. It suggests that we really shouldn't dismiss the possibility of quantum computation in the brain based on simplified models alone. The intense debate over decoherence in the brain really highlights a fundamental difficulty. Biology is messy. When testing a theory like Orch-OR, which combines a claim about fundamental physics, objective reduction, with a claim about biology, namely quantum processes in microtubules, a negative result is always ambiguous. If our mass invariance test fails to show a frequency shift, does it mean the physics of OR is wrong? Or does it simply mean that decoherence is too strong in microtubules and the biological part of the theory is wrong? It would be immensely valuable to find a way to test Penrose's physical prediction, the gravity-induced collapse, in a clean, controllable system, completely separate from the complexities of the brain. And, actually, this is precisely what physicists in the field of optomechanics are now attempting to do. They are designing experiments to probe the boundaries between the quantum and classical worlds using non-biological systems. The goal is to create and sustain a quantum superposition of a macroscopic object, an object large enough for its gravitational self-energy to be significant, and then watch to see if it collapses on its own, just as Penrose predicts. If they can demonstrate that tau equals hbar divided by Eg holds true in a vacuum chamber on a lab bench, it would lend tremendous credibility to the physical foundation of the Orch-OR theory, regardless of whether it ultimately happens in the brain. These experiments often involve using lasers to trap and cool a tiny object, such as a nanoparticle or a microscopic mirror, down to near absolute zero. By cooling it, they remove the thermal vibrations that would cause decoherence. By trapping it in a vacuum, they isolate it from collisions with air molecules. Once the object is perfectly still and isolated, the next step is to use quantum tricks to place it into a spatial superposition, a state of being in two different locations at once. The separation distance might be tiny, maybe only the width of an atom, but for an object containing billions of atoms, this is a massive superposition with a significant gravitational self-energy, e.g. The stage is then set for the crucial measurement. According to standard quantum mechanics, this superposition should last indefinitely as long as it is isolated. But according to Penrose's objective reduction, it has a finite lifetime, tau, determined by its mass and separation. The experiment is designed to hold the superposition and simply wait, watching for the moment it spontaneously collapses. By repeating this with objects of different masses and different separation distances, physicists can check if the collapse time scales exactly as the Penrose equation predicts. This provides a direct, biology-free test of the core physical claim that underpins the entire quantum consciousness hypothesis. Let's imagine one such tabletop experiment in more detail. A team of physicists uses a focused laser beam, an optical tweezer, to levitate a tiny silica nanosphere, about 100 nanometers in diameter, inside an ultra-high vacuum chamber. They use other lasers to cool the sphere's motion until it is almost perfectly still, reaching a quantum ground state. At this point, they apply a carefully timed pulse of light to split the sphere's quantum state, placing it into a superposition of being in two slightly different positions simultaneously. They have successfully created the space-time blister that Penrose's theory describes, but with a glass bead instead of a tubulin protein. Now, the critical observation begins. The experiment is a waiting game. The physicists monitor the sphere's position, looking for the telltale signature of a spontaneous collapse. According to Penrose's equation, given the mass of the nanosphere and the separation distance they created, they can calculate the predicted lifetime, tau. For a typical experiment, this might be on the order of milliseconds to seconds. If, after many trials, they observe that the superpositions consistently decay at or around this predicted time, it would be groundbreaking evidence for objective reduction. It would show that gravity does indeed play a role in resolving quantum uncertainty. These experiments are at the absolute cutting edge of modern physics. They are incredibly difficult to perform, as they require pushing technology to its limits to fight against every possible source of environmental decoherence. However, they offer a clean, unambiguous path to testing the new physics proposed by Penrose. Unlike the messy biological experiment, there are far fewer confounding variables. The mass of the nanosphere is known precisely, the vacuum is controlled, and the temperature is managed. The system is designed from the ground up to be a perfect testbed for fundamental physics. The results of these levitated particle experiments will have profound implications for our original question. If they fail, if the superpositions last much longer than Penrose predicts and only decay due to known sources of decoherence, then the physical foundation of Orch-OR would crumble. But if these experiments succeed, if they confirm the gravity-induced collapse model in a non-biological system, the situation changes dramatically. It would prove that the physical mechanism required by Orch-OR is real. The debate would then shift back to biology, but with a crucial new piece of evidence, the spooky physical process required for quantum consciousness would have been shown to be a genuine feature of our universe. Oh, the stage is set for the definitive biological experiment where quantum gravity meets neuroscience in the lab. Every step is pre-registered and transparent, locking in the protocol before a single neuron is touched. We use cultured neuronal networks or rodent brain slices, split into control and test groups, with every variable tightly controlled. Double-blind procedures and coded samples ensure unbiased results. Multiple control conditions, including unrelated isotopic substitutions and microtubule targeting drugs, guard against confounds. Only with this fortress of rigor can we trust what the experiment reveals. The experiment's heart is isotopic labeling, feeding neurons amino acids with heavy carbon-13 for the test group and standard carbon-12 for controls. Ideally, the heavy isotope targets only the microtubule regions implicated by Orch-OR, isolating the mass change. Mass spectrometry confirms the precise incorporation of isotopes, ensuring no unintended cellular changes. Neuronal health and function are checked. If basic properties differ, the experiment fails. Only when both groups are identical, except for microtubule mass, do we proceed. Now, we search for the signature of consciousness. With verified cultures, we stimulate neural networks and record their electrical activity. Microelectrode arrays capture gamma band oscillations, Orch-OR's predicted signature. We analyze hundreds of trials, measuring the exact gamma frequency for each. The goal: detect a subtle, systematic shift in frequency between groups. Secondary measures, amplitude and network connectivity, help interpret results. Computational theories predict no frequency shift. Orch-OR predicts a change. The data will decide. Thousands of gamma frequency measurements are pooled for blind analysis. The statistician compares Group A and Group B following the pre-registered protocol. Scenario A: a significant frequency increase in the test group. Orch-OR's prediction confirmed. Scenario B: no difference. Computational theories hold. Only after analysis is the code revealed, confirming which group was which. Either result is decisive, a bombshell for quantum consciousness, or a strong case for computation. The experiment forces nature to answer. The experiment's outcome splits the future of consciousness research. A null result strengthens computational theories. Consciousness as information processing, no new physics required. AI and neuroscience double down on replicating the brain's architecture, blurring the line between human and machine. But a positive result, an isotope-induced frequency shift, would revolutionize science. It would be the first empirical evidence linking quantum gravity to consciousness. The mind would be tied to the cosmos, validating Penrose and Hameroff. Either way, the experiment reshapes our understanding of what it means to be conscious. A positive result in the mass invariance test would do more than just validate one theory. It would open up an entirely new field of scientific inquiry, a kind of quantum biophysics of the mind. The focus would shift from mapping the brain's classical connectome to understanding its quantum dynamics. Scientists would race to explore the precise mechanisms of the Orch-OR model. How exactly do microtubules shield themselves from decoherence? What is the nature of the orchestration that guides the collapse outcomes? How does this process scale up from individual neurons to produce the unified, rich tapestry of our subjective world? The tools of neuroscience would merge with the tools of quantum physics, with researchers using techniques from both domains to probe the delicate interplay of biology and space-time geometry. This new paradigm would suggest that life is not just a clever arrangement of classical chemistry, but that it has, through billions of years of evolution, learned to harness the most subtle and fundamental laws of the universe. The unique properties of biological matter, the specific structure of proteins, the behavior of water within cells, would be seen not as incidental details, but as essential components of a quantum machine. It would imply that consciousness is not something that can be easily engineered in any substrate, but that it might be a rare phenomenon, requiring the specific, finely tuned conditions found only within biological systems. The future of AI would be completely re-evaluated. To build a truly conscious machine, we might first need to build an artificial, living cell. The philosophical implications would be immense. If consciousness is tied to a non-computable process involving quantum gravity, it would affirm Penrose's original intuition that human understanding and creativity have a quality that transcends algorithms. It would place a fundamental physical dividing line between the authentic consciousness produced by a biological brain and the simulated intelligence of a digital computer. This could provide a scientific basis for what many have felt intuitively, that there is something special, something irreducible about living, conscious beings. Our place in the universe would be both humbled and exalted, humbled by the realization that our minds are subject to physical laws we are only beginning to grasp, and exalted by the idea that we are direct participants in the universe's ongoing process of resolving quantum reality. Of course, even a positive result would not be the end of the story, but the beginning of a new, more challenging chapter. It would raise countless new questions. Is this process unique to neurons, or could it occur in other cells? Does it happen in the microtubules of plants or other organisms? What is the precise nature of the non-computable element in the collapse? The confirmation of gravity's role would not solve the mystery of consciousness, but it would finally give us the correct language and the right set of physical principles to begin tackling it in earnest. The hard problem of subjective experience would remain, but it would be reframed as a problem in fundamental physics. Regardless of the outcome, the very existence of this thought experiment and its growing feasibility marks a crucial maturation in the science of consciousness. For too long, the field has been a battleground of unfalsifiable philosophical positions. The mass invariance test, and others like it, represent a move towards a more rigorous empirical science. By forcing competing theories to make concrete, distinguishable predictions, we elevate the debate from what if to let's find out. This commitment to experimental falsification is the engine of all scientific progress. Whether the final answer is gravity or code, the act of asking the question in a testable way is a victory in itself, pushing us to refine our definitions, clarify our assumptions, and sharpen our tools. The journey we have taken illuminates the profound depth of the mystery we are trying to solve. On one hand, the computational theories offer an elegant, parsimonious explanation that fits neatly within our current understanding of biology and computer science. They paint a picture of the brain as a magnificent biological machine whose secrets can be unlocked through careful reverse engineering. On the other hand, the quantum theory offers a breathtakingly bold and romantic vision, linking the intimate workings of our mind to the grandest questions of cosmology and the nature of reality itself. It suggests we are more than just machines. We are conduits for a deeper physical truth. So, as we stand here today, on the precipice of what could be a new era of understanding, the question remains suspended in a superposition of its own. Is the secret to your inner world a magnificently complex algorithm running on the wetware of your brain? Or is it a symphony of collapsing quantum states, a gravitational echo that ripples through the architecture of your neurons with every conscious thought? Is the richness of your experience a feature of information or a feature of physics? The truth is, we do not yet know. But for the first time in history, we can see a clear path to finding out. The final answer awaits us, locked away in the subtle difference between a normal carbon atom and its slightly heavier cousin. It is a testament to the power of science that a question so vast, so central to our identity, could hinge on a detail so small. Until that experiment is run and its results are known, the ultimate nature of consciousness remains the most profound and compelling unanswered question in all of science. It is the question of what we are, and it drives us forward into the unknown, armed with curiosity, rigor, and a deep-seated wonder at the mystery of the mind.